For those of you that don't know, I'm a retired college faculty. I did most of my teaching in Kansas, in Manhattan, Kansas, at Kansas State University in geology. And my two areas of teaching and research were, excuse me, were paleontology, paleoecology, so looking at fossils and interpreting them as far as their environments, and the other was paleoclimate, so using various tools to reconstruct climates of the past. So I have some expertise in climate science and climate change. And I have a couple objectives. One is just to give you an overview of the evidence that's out there for climate change, hopefully convince you that climate change is real and that it is a pressing issue, a pressing concern. And secondly, that the consequences of current climate change and projected climate change is for a lot of suffering. A lot of suffering and displacement of people, of economic losses, and that's happening actually now. That's already started, that's already happening now, and it's only going to accelerate, it's only going to get worse, even under the best scenarios. And so it's something, especially as Christians, that we need to be aware of and prepare for. So how is the church going to respond to that? How is the church going to respond to these very large needs of large segments of the population, particularly people who are least able to adapt? The poor, people in minority communities, people in third world countries are going to experience the effects more severely than those of us privileged people in the US. So, with that introduction, first I want to just make a quick point that global warming is nothing new. In other words, the science of the awareness of global warming as a consequence of the burning of fossil fuels is not a new idea. Actually, it was in 1896, a Swedish chemist named Svante Arrhenius was one of the first ones that determined that the burning of coal produced carbon dioxide, and that carbon dioxide in the atmosphere would increase the temperature of the climate, will increase global climate, temperature of the global climate. Interestingly, he thought that it was a positive thing. And then in 1949, a coal engineer, George Callender, compiled all the data that existed at that time on carbon dioxide measurements and temperature measurements, and found that CO2 was indeed rising in the atmosphere and that the temperature of the global climate was also rising. So ever since 1949, 1950, this connection was well recognized and determined. So what's the basis of this? Well, the fundamental part of understanding current climate change is the greenhouse effect. And probably a lot of you have heard of the greenhouse effect. There are a number of gases, carbon dioxide being a main one, also methane, which we'll talk about, and also water is also a greenhouse gas. And what these gases do is they absorb heat. These molecules absorb heat that's radiated from the Earth's surface. So the way this works, the reason it's called the greenhouse effect, it's actually a very appropriate description. If you think of a greenhouse, it has glass walls and glass ceiling that allows visible light to come through. So they're transparent. So visible light comes through, that light then impacts the surfaces in the greenhouse, so the floor and the bricks and the plants and everything absorb that light, that visible light, and they re-radiate it out as heat, as infrared. But the glass is an insulator, and so it holds the heat in the greenhouse. So you can think of greenhouse gases as being like the glass in a greenhouse. So solar radiation comes in from the sun through the atmosphere, so the visible light comes through, reaches the surface of the earth, absorbed by all the various things, animals, plants, dirts, rocks, ocean, water, absorbs that light and re-radiates it out as heat, as infrared that goes back up into the atmosphere, and then it's trapped, it's absorbed by these greenhouse gases. And the more greenhouse gases you have, the more that heat is absorbed. The point here, one point here is, without the greenhouse effect, the Earth would be basically a solid ball of ice. In other words, the greenhouse effect is absolutely essential for the existence of life on Earth. The problem is that we've accentuated its impact. So then the question is, okay, where does the CO2 come from and where does it go? Anytime you're talking about things like this, you have what's the source of that element and how is it removed? How is it added? How is it removed? So what are the sources of carbon dioxide and methane, the two main greenhouse gases? Well, there's wetlands. If you walk through a wetland, you walk through the water's black, the mud's black. You walk through it and you'll smell this kind of rotten egg smell. Okay, that's because that mud has a lot of organic material in it. Okay, that's why it's black. Okay, so that's being kept there and it doesn't oxidize. It's anoxic, so it just accumulates. So wetlands are one place. Interestingly, termites. There's a huge volume mass of termites globally. And any insect, and actually any animal, as we'll see, that digests plant material, particularly fibrous plant material, can't do it without bacteria. And bacteria is anaerobic bacteria, and it lives in the guts of the animal. So it lives in the guts of termites. Termites could not digest wood if they didn't have these bacteria. Those bacteria, as a byproduct of digesting the wood, release methane. And the same thing happens with ruminant animals. So that's a field of wildebeest in the African veldt. Ruminant animals, like cattle, again, harbor these bacteria in their guts that help them, enable them to digest the grasses that they're eating, and they belch out huge volumes of methane. And particularly early on in Earth history, one of the main sources of carbon dioxide was volcanic eruptions. Where does it go? So those are carbon sources. What are the carbon sinks? How is it removed from the atmosphere and where does it go? So things like peat. So in kind of particularly northern climates, cool climates, kind of peri-Arctic climates, decomposition occurs very slowly. Organic matter builds up into a really thick layer of organic matter that we call peat, that for a long time was harvested both for a lot of reasons, both including to burn for fuel. Another important thing is, well, as we'll talk about, is permafrost. That is the frozen soils that, as we'll see, cover a large area of the northern continents. And those ices contain methane. Methane is trapped in the ice. And so when the ice melts, that's released. And when the permafrost forms, that traps the methane. This is a methane sink. Trees. The world's forests are a huge sink for CO2. You all know that, right? Trees take in carbon dioxide, and through the process of photosynthesis, they release oxygen. And so they're a huge sink for CO2. What changes is what's called the total standing crop, or total biomass of all the trees in the world. And it's when that biomass changes that it has an impact on climate. So if you cut down a tree and plant a tree in its place, that's net zero. It doesn't change. But if you go into the tropics and you cut down a tropical rainforest, now you've removed all of that storage, all that carbon storage. Coal and all the other fossil fuels, so coal, gas, oil, all were originally produced by plants or algae and plankton in the oceans. And when they die, they accumulate, and depending on whether it's on land or in the ocean or what the materials are, what the plant materials that are accumulating, you get coal or you get oil, you get gas. But all the carbon and all the coal in the world, all the oil in the world, all the natural gas in the world, all that was originally in plants, and those plants got their carbon from the atmosphere. So imagine that all the coal, all the fossil fuels in the world, globally, all that carbon originally came out of the Earth's atmosphere over millions of years of time. So when we burn those things, what we're doing is we're releasing really, really old carbon that used to be in the atmosphere, and we're putting it back in the atmosphere really, really fast. Other sinks, the ocean. The ocean absorbs a very large, I think something like 30% of the CO2 that's produced is absorbed by the ocean. So the oceans are a big sink, but it's a limited sink. Oceans will have a limit to how much they can absorb. Again, black shales, any of these black sediments, that black is carbon. Limestones, all the limestones, all the reef limestones, all the fossil shells, that's all, again, that's carbon, that's calcium carbonate, but the carbon in that originally came from the oceans, which originally came from the atmosphere. So again, it's all atmospheric carbon. And then there's something interesting called clathrates, which are shown in the lower left, or methane ices. And these, again, can be in permafrost. They're also in the bottom of the oceans. The bottom of the oceans are very, very cold. And so these ices are forming and incorporating methane, and there's so much methane in those ices that you can light it. That's a picture of those pieces of ice that are burning. There's so much methane in the ice that it will actually burn. Okay, so what are the anthropogenic sources? Those are the sources that we produce, human civilization produces. Well, kind of imitating the wetlands, rice paddies. It's an enormous area of the surface of the earth that's covered by rice paddies and wetland crops. So they're producing methane just like wetlands do. Again, all the fossil fuels, cutting down forests, particularly tropical rainforests, and our vast number of livestock, particularly those that are raised like this in large compounds. So they're not free-ranging, they're in these enormous paddocks. And the number of cattle that are raised in the world far exceeds the number of ruminant animals that existed naturally. All right, so I know that took a bit of time, but I think that's important to set that precedent. So try to go a little faster. This is a picture of increasing CO2 from 1960 to now. And what you can see, this is from, recorded from the top of Mauna Loa in Hawaii. It's been in operation for a very long time. And you can see that it's a very steady, even accelerating increase in the carbon dioxide concentration of the atmosphere. What you notice, which is kind of cool, is it has this sawtooth pattern. Any idea why? Close, yes. During spring and summer, plants leaf out. This is the northern hemisphere. Deciduous plants leaf out. They start photosynthesizing, and they're taking carbon out of the atmosphere. Then in fall, they drop their leaves. Now that sink is gone. They're no longer taking CO2 out of the atmosphere, and the CO2 concentrations rise. So each one of those little sawtooth is 1 year. So the peak is winter, and the low point is summer. So, okay, what about a longer time frame? Well, in the lower right is concentrations of CO2 for the last 1,000 years. And what you see is up until about 1769, it's pretty flat. And then it goes up. Right now, the current concentration of CO2 in the atmosphere is 420 parts per million. This says 400. So this line here would go up about to there, would go off the top of this chart for current, right? So we have this very sudden rise in CO2 in the atmosphere. Any idea what 1769 is? That's the invention of the steam engine. So that's the beginning of the Industrial Revolution, and at that point, you see this beginning of this rapid rise. And on the left is methane, and methane follows a very similar curve. What about if we go back further? This is taking carbon dioxide concentrations back 800,000 years. And I can go, questions later, I can explain how these values are, whoa, that doesn't show very well. Why is that? I don't know why. Maybe you can make it out. I don't know why. But so you can see the line here, right? That's the highest previous to now. And then here, remember, it's 420. So again, this last line goes up to about here, right? So over the last 800,000 years, right, the amount of CO2 in the atmosphere now far exceeds anything that's existed in the last 800,000 years. So what about temperature? Well, here is temperature. This is from 1850 to 2023. And again, what you see is relatively flat, actually a bit of decline in temperature here. And then from about the turn of the century on now, there's some plateaus. We have this very steady increase, even accelerating increase in temperature. This is this year. So this year will be by far the highest global temperature, average temperature on record. One point here is, notice that there's a lot of noise here. Some people expect, well, if global warming is correct, that there should be a nice smooth curve. Well, you have a nice smooth curve for the introduction of CO2, but there's a lot of other complicating things going on. There's a lot of things that impact the global climate in addition to greenhouse gases. And so that creates these fluctuations. But it's long-term trends that matter, not year to year, not decade to decade, but over a long period of time, what are the trends? That's what you have to pay attention to. Here is global temperature now for the last 11,000 years. Interesting point is 8,000 here. Before that was the last ice age, which ended about 10,000 years ago, at which time the global temperature was about 8 degrees C colder than it is now. That's all. 8 degrees is the difference between now and the height of the ice age, only 8 degrees. The Earth's climate is very sensitive. And what this line here is, this is coming out, would be way down here, this is coming out of the ice age. Typically, the way this works in cycles, comes out of the ice age, it reaches its peak, and then slowly declines back into another ice age again. And that's what it was doing. See, so here, 8,000 years ago, maybe 6,000 was at the peak, and then it started declining until just about 100 years ago. And again, this temperature now, this says 0.04. We're almost at 1.4 right now. So if you're going to do this line, it would be like up there. Okay? So it's actually reversed the trend that was occurring before, and now it's spiked way up. Okay, now I'm going to look at, so what are the impacts that we see right now? Now, I'll go through these fairly quickly, but this is just the impact of heat itself, just air temperatures impact on human bodies. And it's generally said that any consistent temperatures above 95 degrees Fahrenheit are detrimental to health if you don't have air conditioning, if you don't have ways of cooling off. And so these are all cities in the US that recording the number of days in the year that are 95 degrees or more. And again, you can't see the numbers, unfortunately. And so what it shows is you trace these across, and over from 1976 to 2023, all these cities have a substantially larger number of days above 95 than they did previously. Okay, so that means that the danger to human health, the risk to human health are substantially higher now than they were a number of decades ago. I'm sorry these graphs aren't showing very well. Next thing is sea ice loss. So this is in the Arctic. And in the Arctic, the sea ice grows and shrinks annually. So in the fall and the winter, the ice freezes, the extent of sea ice in the Arctic grows. During the height, it will extend out, covering most of the Arctic Ocean. And then in the summer, it starts melting back. And what this graph over here shows, again, this is from the years are 1870 to 2010. That's 1817, 2010. And this is the number of square kilometers that are covered by ice during the ice minimum. So when the ice melting reaches its greatest extent. And what you see, again, is this first gradual and then accelerating loss of sea ice in the Arctic. And as we'll see, that can have a lot of, quite a wide range of impacts. One thing that it does is, one thing you have that's very important for understanding climates are something called feedback systems, positive and negative feedback systems. And sea ice is one of those positive negative feedbacks. So this is just the same year, showing what extent during the greatest extent of sea ice versus the minimum, right? So you can see the difference. Something called albedo is how shiny or how reflective the surface of the Earth is. The more sea ice there is, ice and snow are very reflective. That's why they're white. They're very reflective. They're reflecting almost all the light back into the atmosphere. And so if you have a lot of reflective surface, a lot of that light is not absorbed by the surface, so it's not turned into heat, and it's just reflected back out into space, and it's lost, right? The less ice you have, the more darker surfaces. Notice how the ocean here is much darker than the ice. All that ocean surface is absorbing heat. So the more exposed ocean you have, the more heat is being absorbed by the Earth's oceans, and that heats the global climate. So the less ice you have, it's a feedback system. So you have less ice, more heat is absorbed. That means you have less ice, which means more heat is absorbed, which means you have less ice. That's called a feedback system. In addition to sea ice, glacial ice is melting. This is Greenland. This is the Greenland ice sheet, or ice cap. And this is the loss of ice mass on Greenland, which again is on a steady decline. And again, this is, melting sea ice doesn't change sea level, because it's like you put ice cube in a glass of water and then let the ice cube melt, the level of the water in the glass doesn't change. Okay? So floating ice doesn't change, melting floating ice doesn't change how much water is in the ocean. Melting glaciers does. Okay? So all the melt that melts off of Greenland is raising global sea levels. And similarly, Antarctica. That's grounded ice as well. And the same thing is starting to happen in West Antarctica. The western part, western third of Antarctica is experiencing a fairly significant ice loss. And there's actually one really big glacier. It's been called the Doomsday Glacier because it holds so much ice. And just in the last few years, recent research has been able to look underneath it and take submersibles underneath it and instruments underneath the ice, and determining that it's unstable. And so it's reaching what's called a tipping point, perhaps, which means if it starts to, it is losing ice, but if it reaches a certain point, it can do that uncontrollably. And so it doesn't matter what we do about the CO2 levels in the atmosphere, it's going to melt completely. And that's another concern. There are a lot of these what are called tipping points, and we don't know exactly where they are. Here's some, you can go on the internet, there's lots of these kind of pictures. These are alpine glaciers. This is one in the Swiss Alps. Again, between 1856 and 1987, taken from exactly the same location. Alpine glacial retreat is happening globally. This is in Alaska. the Pedersen Glacier. This is 1940 on the left and 2005 on the right, again, taking from exactly the same location. One of the potential problems with glacial melt is communities that live in alpine areas that are dependent on those glaciers for their fresh water. The glaciers are the only source of fresh water. And this creates kind of a conundrum. When the glaciers are rapidly melting, they get more water than they want, and there's the danger of floods. Okay, that's what's shown on the left. That's a recent one in Himalayas of a glacial lake dam that burst, and there's also a glacial avalanche associated with it due to the melting of the glacier. On the right is an example of a glacial melt lake that's being drawn for fresh water. I don't know if you can see it, but these are all pipes coming out of the lake that are providing fresh water to that community. When that glacier melts away, there won't be any more water. And these are the only water sources for these mountain communities. Another thing that's impacting the Arctic is permafrost. I talked about permafrost before, and you can see it is a huge area of the Arctic. All that purple, that's all permafrost. There's Russia, and here's Canada and Alaska. It's a huge area. And that permafrost is holding a lot of methane. And what's happening is that permafrost is melting, and in the process, it's releasing methane. So this is a little maybe hard to see, but this curve is a curve of the temperature of the ground in Fairbanks, Alaska. And this line here is the 0 line. That's 0 degrees. Okay, that's freezing, 0 degrees C. And what you see is, as you're moving, again, this 1930 to 2000, the ground temperature is warming until you get up here in the 1990s or so, and now the ground temperature is above freezing. So that means you're melting the permafrost. This is what melted permafrost looks like. This is happening in Siberia, it's happening in Alaska, it's happening in Arctic Canada. And so these are all melt pools. As that permafrost is melting, the ground becomes mud and collapses. This is an area called the taiga. It's an Arctic forest, a boreal forest. And notice that the trees are all leaning in all weird angles. And that's because they were originally rooted in permafrost. And that permafrost melts, and there's nothing to hold the trees up, and the trees start falling over. And there's been some really spectacular things happening in Siberia. This has happened over about the last 10 years. And these are gas hydrate explosion craters. And again, there's permafrost. Actually, in this case, they're kind of big masses of ice that are buried under soil. And it's warming up, and the ice starts melting. It releases methane, but the methane is trapped because there's this thick layer of mud and sediment on top that keeps it trapped. And the methane builds up, and the methane builds up, and then eventually it explodes. And it creates these very large explosion craters. Those are people, to give you scale. These things are hundreds of feet deep, 100 feet across. And they're popping up all over Siberia. Causing big problems in places like Alaska, collapse of roads, buildings. Again, essentially your foundations are washing away. Methane is also being released from lakes. This is a National Geographic picture. These bubbles, this is ice, these are bubbles in the ice, and those bubbles actually are filled with methane. And that's what's over here. This person has a digging iron, and this person has a little flame, and the one person takes a digging iron into one of these frozen gas bubbles and hits the flame, and it explodes to show that the gas in these bubbles is actually methane. So what about sea level rise that I mentioned? That's also accelerating. Most of this, until quite recently, most of the sea level rise, which you would think is relatively small, you're talking about millimeters a year, this is globally, is from heat expansion. The oceans are getting warmer, warm water expands, takes up more space than cold water, and so even without any new water being added to the oceans, sea levels are rising just because the ocean is expanding. But now in the recent decades, added to that is now meltwater from glaciers, from Greenland, from West Antarctica, and that's going to accelerate. So as that accelerates, that melting is going to overwhelm just the thermal expansion. This gives you an idea. This is from the latest report of National Oceanographic Administration on projected sea level rise by 2100. It says about 2 feet of sea level rise along the US coast is increasingly likely by 2100 because of emissions to date. So that's saying if we stop producing CO2, we stop burning fossil fuels now, worldwide, which obviously isn't going to happen, right? But just the CO2 that's already in the atmosphere will generate a sea level rise of about 2 feet by 2100. Then it says failing to curb future emissions can cause an additional 1.5 to 5 feet for a total rise of 3.5 to 7 feet by the end of the century. And that's still a fairly favorable scenario. Well, what's the big deal about sea level rise? There are an awful lot of communities, coastal communities, island communities, that are effectively only feet above sea level. Large populations are just a few feet above sea level, including in the US. People love to be at the seashore. And so this was during just a nor'easter on Massachusetts, and you'd see the waves pushing water into the residential area. This was after Superstorm Sandy, which you might have heard of a while back in Jersey Shore. Again, these are these coastal communities, and again, this is just rising sea level from storms, called storm surge. I'll talk about it more in a little bit. Actually, it's very relevant today. So again, a sea level rise of 3 to 5 feet, all these communities are going to be underwater. And there are particularly small island communities in the Pacific that are only a few feet above sea level that are highly at risk. And they are making desperate pleas to the rest of the world because their very existence is threatened. And again, Alaska, both the combination of sea level rise and the loss of sea ice, which protected the coast, but now that sea ice is gone, and now waves can cut into the edge of the coastline. This is not quite up to date, but it's close. Um, Again, there's a whole lot of lines, squiggly lines here, which represent the ocean. This is ocean temperatures, not air temperatures. But what's happened last year was the largest deviation from previous ocean temperatures on record. And this year, we're doing one better. Okay? So the last 2 years, it's been gradually increasing from about here to here, but the last 2 years, in other words, it seems to be accelerating. What's the big deal about sea ocean temperatures? Lots of ocean life is impacted by water temperature. One of the most sensitive groups of organisms are corals, reef-building corals. And when they're very temperature sensitive, and once the temperature reaches a certain amount, they get stressed out. And when they get stressed out, they force what are called zooxanthellae, which are algal cells that live within their tissues and are actually important for the health of the corals. And when they're stressed out, they expel those algae from their tissues, and the result is they turn white. And it's called bleaching, coral bleaching. And they can recover, corals can recover from bleaching if given time. But if bleaching events occur, if they're severe bleaching events and they occur repeatedly, it will kill the corals. This gives you an idea, and this year, global bleaching event has impacted more than 72% of the world's coral reefs. And there are large areas of dead coral in the Great Barrier, in the Caribbean, elsewhere. Briefly touch on this one. This is actually one that kind of scares me the most. There's something called thermohaline circulation. Not only are the ocean currents moving around horizontally, we know like the Gulf Stream and so forth, right? We're all familiar with how the ocean is circulating at the surface. But not only is it circulating at the surface, it's circulating vertically. And the way that works is you have warm air or warm water, surface warm water that comes up. This is a Gulf Stream here, comes up into the Arctic on either side of Greenland. And when it's winter and it's freezing, sea ice is forming. When sea ice forms, it excludes most of the salt. So the cold water right underneath the ice becomes saltier, which makes it heavy, and it sinks. And it sinks to the bottom of the ocean, and it travels all along the bottom of the ocean until it comes up again in the southern hemisphere. If you both significantly decrease the amount of sea ice, as well as start flowing cold, fresh water off Greenland, that water now floats. Okay? It's cold, it's fresher, and it won't sink. And what that does is it shuts down this circulation. And that's happened in the Earth's past. We know that's happened in the Earth's past. And it's not a good thing. It has real wide impacts globally to global climates because it changes temperature patterns and can have a very significant impact. So what about other things? As climate warms, the vegetation zones in the Earth shift. And those of us that are paying attention to native plants and things, notice that there's been a change. Things are moving. Some things that lived here are stressed out now and so forth. So basically, plant communities are shifting. And this is a really interesting, the UK is great at recording stuff like this. They've been recording the bloom times of flowers back into the 1700s. They have this huge, long record, right? And the earliest flowering dates, it says in January 2015, 368 plant species were in bloom in the UK in January, compared to 20 50 years ago. In other words, everything's blooming earlier because spring comes earlier. And this is a published plant hardiness zone. This is USDA, United States Department of Agriculture. This is a 1990 map showing the various vegetation zones. This is a 2015 map. I couldn't get a 2020 map. And what you see is, if you just look closely, that these vegetation zones have migrated almost the width of a state in that time period. So if you look at Pennsylvania, here in southeast Pennsylvania, it's this light green. Now it's yellow. Okay? So there's been noticeable, and this has impacted agriculture. And again, this didn't come out very well, but this shows agricultural areas today. So this is Africa, South America, North America, Asia. And the brown colors here are places where agricultural production is expected to decline because of these changing climate zones. The green areas are where agricultural production is expected to increase. In other words, conditions for agriculture are better. So what that means, for example, in the US would cease to be the breadbasket of the world, and Canada would now be the main producer. Okay? And in Europe, I mean, and look at the southern continents. Africa, there's like hardly any green at all there, right? Asia, China, India, all these high populated areas would all decline in production, whereas the northern, like Northern Europe, Northern Asia, Canada, would be now better. So this suggests a huge economic agricultural switch. In other words, as far as what countries are producing and which are now dependent on other countries. Migration. Changing climates impact timing of migrations. And it impacts their success of migrations. And this, again, is already being monitored. Change in disease vectors. Again, as organisms are moving around, adapting to changing climates, along with plants and flowers and things moving, so are disease vectors. So, for example, tick-borne diseases are moving north. Mosquito-borne diseases are moving north. So diseases that once were Central American or South American are now making appearances in the US as these disease vectors move to the north. Climate change can also cause plagues. This one happened in 2019-2020 in East Africa and Arabia. It's a locust plague. And interesting how that happened. This happened the year before. This was a cyclone what we call a tropical storm, that impacted the Horn of Africa and actually Arabia and to the Arabian Peninsula over here. That doesn't happen very often. And actually, there's been more of these kind of odd events, storm events like this that you would not expect to be in that location. So what it did is it caused a plant bloom, right? Deserts finally get a heavy rain, seeds that have been lying fallow suddenly burst into bloom, everything greens up, and the grasshoppers and locusts say, wow, we've got it made, and it causes a plague. Changes in climate affect things like the pine beetle infestation that's wiped out millions and millions of pine trees in the West. These brown are all dead trees. Those beetles have always been there. This is a pine bark beetle. They've always been around. What's happened is the winters aren't as cold, so they don't die. So they survive, more of them survive through the winter, so in the spring there's a larger pool to start the next generation. And as a result, it's caused widespread tree death out west. Another thing characteristic of climate change is, current climate change, is increasing desertification, increasing deserts, or increasing droughts, I shouldn't say deserts, increase in droughts, both the number and the duration of droughts. And we've seen that in the US West. That drought is now ended, but there was a very long drought. It's still, the water levels in like Colorado River are still highly depressed. And these are areas that are experiencing current droughts. And with those drying conditions, increased fires, which you probably are aware of. And yes, there are more and larger fires starting earlier in the year, lasting longer in recent years. That's a real trend. And fires are even increasing in the Arctic. The one on the right is Arctic tundra fire in Siberia. And so this is in Siberia. This is in the rainforest. There's a lot of burning going on in the rainforest due to slash and burn agriculture, wiping out rainforest and using it for agriculture. But these are natural started fires due to drier conditions. Flooding. Flooding events are getting worse, more severe. Why is that? Some people get a lot of response from people, wait a minute, increases droughts, increases floods. This doesn't make sense. How can the same thing cause two opposite effects? The reason is the warmer the air is, the more water it can hold, right? Which means it can evaporate more water. So if you're in a warm area, in desert or near desert area, the air now can suck up even more moisture, which makes it even drier. But when it rains, there's more water in the atmosphere to come out. So when it rains, you actually get more rain, and when it doesn't rain, it's drier, and you have more evaporation. So you get both more evaporation and heavier rains. And the point here for this one is that almost always these events impact low-income communities the worst. And this is just one example. This was a couple years ago in Kentucky, some widespread flooding from a rainstorm. And the areas that were flooded, for example, this town, Beattyville, Kentucky, in that town, nearly 40% of the families in that community made less than $10,000 a year. Why? It's because low-income populations, homeowners, get the cheapest land. And it's usually near in floodplains and other areas that are at risk. And so they are the ones that experience the worst effects. These are this year. Unusual flooding in Bangladesh, in Central Europe, if you saw that in the news, just a big weather system that just sat over Central Europe. I think there was places that got like 20 inches of rain, just astronomical amounts of rain. Hurricane intensities. Tropical storms feed off of warm ocean water. That's where they get their energy. They get their energy from evaporation. So the warmer the water is, the more power there is, the more energy there is for a tropical storm. There was a lot of debate early on by climate scientists about whether this would increase the number of tropical storms or the intensity or both. And it seems pretty clear now from evidence for the last several years is that these storms, the impact is not an increase in the number of storms. In fact, they can even be depressed. Right now they're being depressed because there's dust blowing off of northern Africa into the Atlantic Ocean, and that atmospheric dust is actually inhibiting storms. But when one gets started, as soon as their conditions are right to get one started, they do what's called explosive intensification, rapid intensification. Right now, as we speak, is Hurricane Helene, which experienced 2 phases of rapid intensification, is going to come into Florida certainly as a Category 3 storm, perhaps a Category 4 storm right now. I didn't check the last thing. It's Category 4? Right now. We've had 8 storms so far this year. 5 of those became hurricanes. Now 2 of them have become Category 3 or 4 or 5 storms. In other words, very, very intense hurricanes. And I think 3 of those storms had rapid intensification. It's becoming very, very, very common. The ocean is so hot, the Gulf is so hot, that once a storm gets going, it just spins up really fast. I'm sure you're aware of Katrina. The reason I put Katrina in is that this is another really good example of how these disasters impact the communities least able to deal with them. In New Orleans actually is almost all below sea level, believe it or not. The city is surrounded by levees. It's actually a bowl, below sea level bowl. It's surrounded completely by levees. And they have run pumps all the time to pump the water out so that the bowl doesn't fill up with water. In Katrina, the levees broke. The water poured into New Orleans. And the lowest areas in New Orleans is where the African American communities were. It was those communities that were wiped out. And the more affluent communities were on higher ground, and they were saved. And that happens again and again and again and again. This is a couple years ago. Honduras and Guatemala were hit by Hurricane Eta, and for just complete widespread devastation. Villages, communities completely devastated. Following that, like the next year, a substantial portion of the immigrants that were trying to get into the United States and the southern border were from Honduras and Guatemala because they had nothing left. Their communities were completely wiped out, they had no resources, and they came to the US in desperation. And those are called climate refugees. And it's predicted that climate refugees are going to accelerate. And we're talking about hundreds of thousands of climate refugees worldwide, maybe millions. They're going to be moving. There's already a huge refugee problem, but these refugees are going to be moving, trying to go to places where that, like United States and Europe. And this is a huge problem. This is an enormous problem. Okay, I'm going to end with this, and then I'll open it up to questions. This one, the next one. One of the best sources, and I have books on that one table back there you can look at, as well as some pages that list resources, resources that I'd recommend, various kinds that can provide a lot of information. The IPCC is an international organization that meets every so many years, and all they do is they compile all the research that's been done. We're talking about thousands and thousands of research reports, hundreds of authors just for the IPCC reports, dozens of countries. It's one of the most incredible scientific statements of scientific consensus that you'll find anywhere. I know of nothing similar to it. And so these documents are really important. If you talk about what's one of the highest sources of authority for these kinds of issues, the IPCC is up there at the top. Interestingly, because there's so many people involved, when they publish an IPCC report, all the authors have to agree on every word in the document. What that means is it's conservative, right? So the extremes are gone, right? So it'll tend to go in the middle, right? Well, I really wish you would put this in, but you can't get enough people to agree, right? So they're actually conservative, and the IPCC has consistently underestimated climate effects, simply because it's conservative. It's going to almost always underestimate. And so here is the last report. This just came out. The best estimates for future warming, again by 2100, are 1.4 for very low greenhouse gas emissions. That is, no more greenhouse gas emissions, which is obviously not going to happen. The previous target was 1.5. We'll probably be over 1.5 in a few years. 2.7 degrees C for the intermediate scenario, and 4.4 C for very high greenhouse gas emissions. This is probably perhaps the current most realistic one. And so 2.7 to 3 degrees C implies some very, very severe impacts. Scenarios consistent with continuation of policies. That's just if all the nations were faithful to all their written commitments so far, right? That would lead, by the end of 2020, to global warming of, in other words, continuation of policies in place by 2020 would lead to global warming of 3.2 degrees by 2100. That's if everybody does what they say they're going to do, expected 3.2. Best estimate for reaching 1.5 degrees C, which was the old target, the first half of 2030s, so just in a few years from now. Okay, so what happens, so here, these are some things, maybe I don't need to go through them, you can read them, but risks for warming by 2.0, which we're probably easily going to exceed by 2100. 14% of species in terrestrial ecosystems have a high rate of extinction. Coral reefs projected decline by 70 to 90%. Most low-level and small glaciers will be gone. You go to Glacial Park and there won't be any glaciers left. That's getting there almost now. Loss of snow melt for irrigation, again, things I've talked about. If you go up to 4 degrees C, local extinction of 50% of tropical marine species, biome shifts across 35% of the global land area. Approximately 10% of global land is projected to face increasing high and decreasing flow. In other words, both drought and floods, affecting over 2 billion people. 4 billion people projected to experience water scarcity. Burning areas increased by 50 to 70%. Again, relative sea level rise will be causing infrastructure problems globally. That's pretty scary. One thing I've been impressed with in recent conversations with some people we know and reading literature and so forth is there's been, for too long, there's been an inappropriate degree of optimism. Yeah, we could still make the 1.5. Oh, just need to knuckle down and we'll get the 1.5, or we'll get to the 2 or whatever, and not looking at the flip side of that coin, which is what happens if we don't make those goals. How are we going to deal with the consequences? And I think particularly for the Christian church, that's an important thing to think about and to pray about, and to, how is the Christian church going to respond to increased flood of immigrants, of even internally displaced people. When Katrina hit New Orleans, there's a substantial population from New Orleans that left New Orleans and never came back. We were in Kansas when that happened, and there was a large group of New Orleans residents that ended up in Kansas, and they didn't go back. Some went back, a lot of them didn't. Those are climate refugees, even if they're internal. So what do you do about people moving around, displaced people? What do you do about the people least able to withstand the impacts? So right now, in Florida, Georgia, Tennessee, what's the Christian church going to do with people that are now lost homes, lost property, lost businesses? They're expecting as much as a 20-foot storm surge. That's sea level rise 20 feet. That's over the top of a 2-story building, right? So how many coastal communities are going to be completely wiped out? And what do we do about that? How do we respond to that? Do we take the usual or kind of human instinct and put up your walls and say, I'm okay, get out of here, I don't want to deal with you, I have what I need, I don't want to give up my privilege in order to help you, and so put up walls. That's happening in Europe, all over Europe, it's happening in the US, it's happening globally. Because of this influx of immigrants, people are putting up walls. Or do we open up to the extent that we can and welcome the immigrants and welcome the displaced people? I mean, there's a whole host of really significant questions in there that I have no answer for.